All right, picking up where we left off in the notes last Thursday with Miss Stoltz, you guys were talking about special right triangles, and you had started to talk about, you had figured out in your homework investigation that this pattern always works. Anytime you have an isosceles right triangle, anytime your triangle has two sides congruent and it's got a 90-degree angle box, that the other two angles will automatically be 45 and 45 degrees because the base angles have to be congruent, which means that two sides will be the same since it's an isosceles triangle, and that the hypotenuse every single time will be a square root 2, that same amount square root 2. Okay, so today we're going to look at, here I have a 45, 45, 90 triangle, right? Because this angle's 45, that one's 90, and all angles in a triangle have to add up to 180. I only have 45 degrees left, right? So again, it has to be isosceles because the base angles are congruent, the sides must be congruent. So if this is x, this is x, but dun dun dun, look at my hypotenuse. This should be x square root 2, right? And in this case, it is not x square root 2, it's a whole number, it's 7. So what do you do if your isosceles right triangle doesn't fit the pattern? Well, so is it still similar to this triangle? We know because of angle, angle, squiggle that they have two angles congruent. This one has those same two angles congruent. That these triangles have to be similar. So what do we do when we have similar triangles? We use a proportion in order to figure out what those sides would be in order to solve for the missing legs. All right, so here we go. It says find the value of each variable. If your answer is not an integer, leave it in simplest radical form. So we're going to say that this other side is x, and so the proportion we would use, since we have a similar triangle, since it's similar to this one, where the two sides are the same and the hypotenuse is 1 square root 2. Now, let me pause here for just a second and talk about 1. I just made up 1. This number could have been 6, it could have been 7, it could have been 10,000. It doesn't matter. On a 45, 45, 90 triangle, this pattern will always work regardless of what this number is. So why 1 then? Well, because 1 is a very nice, easy number. So I like to work with it just because it's easy. So I just made this triangle up. I said it's going to be a 45, 45, 90 triangle that follows the pattern of 1, 1, 1 root 2, and it's similar to this triangle. So let me set up a proportion. 1 is to x as square root 2 is to 9, and now I can solve for what that x is. So 1 is to x as square root 2 is to 9. So we know what we do. We cross multiply. We get x times square root 2. Ooh, now this looks like what we did on our very front page when we practiced this algebra, right? Isn't that this scenario right here, except for instead of 5, we now have a 9. So how did we solve this? We divided both sides by square root 2. So let's do that here on our problem. In order to get x by itself, we divide by square root 2. So now x is by itself on the right-hand side of the equation, but oh no, I have a radical in the denominator. How do I get rid of it? Well, I rationalize. I multiply by square root 2 in order to make this a perfect square on bottom so that I don't have a square root on the bottom. So if I multiply across, I get 9 square root 2, and on bottom we've figured out that square root 2 times square root 2 is 2. So that is saying, my friends, that if your hypotenuse is a whole number, as in this scenario, then the legs are not whole numbers. The leg is 9 square root 2 over 2. All right, let's try that out again. In fact, I'm going to pause the video and give you a second to try. Okay, so hopefully you paused the video for a second. You tried the try all by yourself for just a second. So I forgot to use my similar triangle over here. I drew it over here separate, by the way, in case you were wondering what that extra triangle was there for at the bottom. So this time I'll remember to use it. So again, my similar triangle, I'm going to use 1, 1, and 1 square root 2 on the hypotenuse, but it doesn't matter. I could have used 3, 3, and 3 square root 2, right? So my proportion would look like this. It would be x is to 1 as 18 is to square root 2. That's not the only correct way to set it up, but that's one correct way. X is to 1 as 18 is to square root 2. Again, we cross multiply. X times square root 2 is x square root 2. 18 times 1 is 18. Again, to get x by itself, I divide by square root 2. These square root 2's cancel, and I get x equals 18 over square root 2. But oh no, I've got a square root 2 in the denominator, so let's multiply. Let's rationalize the top and the bottom of this fraction by multiplying by square root 2. So I'm going to go over here to the right. That gives me 18 square root 2. When I multiply my tops together, we know square root 2 times square root 2 is 2. Huh! Interesting! Interesting! 9 square root 2 over 2, 18 square root 2 over 2. Do you notice a pattern when my hypotenuse is a whole number to start with? What happens to the other two sides? Is it perhaps that they become that hypotenuse square root 2 over 2? Yes, it is, friends. If your hypotenuse is some whole number x, then the other two sides, the congruent sides, become that number square root 2 over 2. So that pattern also works. Now, it may be bothering you, some of you right now, that I did not finish this problem because 2 goes into 18. This is technically 9 square root 2. For the final answer, this 2 goes away when you divide it into 18. But, I mean, it's the same thing. The pattern still works. You just have to reduce it in the end. All right, so here we go. Let's dive into a word problem. You're designing a dinnerware. What is the length of the side of the smallest square of the plate which a 10 centimeter chopstick can fit along a diagonal without any overhang? So we have a square dinner plate. I like square dinner plates. I think they look nice. And then here's my little red chopstick, right? All right, so round your answer to the nearest tenth of a centimeter. So we're asking ourselves, what is the side length of my dinner plate? And because it's a square, we know that all 4 sides would be the same amount. And because it's a square, we also know that this is a right angle. Huh, would you looky there? I have 2 sides the same length and a right angle. This is an isosceles right triangle, or in other words, a 45, 45, 90 triangle. All right, so let's go back to my shortcut. When my hypotenuse was a whole number, in this case 10, both the sides are that same number, so in this case 10, square root 2 over 2, right? Now, lucky for us, this is a word problem, and you will never hear somebody in real life say, that plate is square root 2 over 2, 10 square root 2 over 2, long for the side length. No, people don't say that in real life. So let's go to our calculator and let's figure out what decimal this is. So I also didn't reduce to start with, but that's okay. Here we go. 10 times the square root of 2. Remember to arrow to the right to get out from underneath the square root, and then divided by 2. So my side length for my plate was approximately, where'd it go? 7.1, we'll call it, to the nearest tenth of a centimeter.